And over the long term, the biggest culprit is carbon dioxide. That's the stuff we mostly get from burning fossil fuels, burning oil, coal, petrol, diesel. The reason it matters the most in the long term is because it stays in the atmosphere for such a long time. You put this stuff up there, it'll be there for hundreds of years. Part of it will be there for thousands of years. So it just builds up over time. And we've now got a situation where we have more of this stuff in the air than the Earth's known for something like 3 million years. So we're really pushing hard on the climate system at the moment, and the climate is changing rapidly. And this was the message from this report that you've just heard about, the Intergovernmental Panel on Climate Change, that came out, or the first part of it that I worked on came out about a year ago. And it was saying that these recent changes in the climate are, so I'm just reading from my notes here, widespread, rapid and intensifying, and unprecedented in thousands of years. So the composition of the atmosphere is unknown for millions of years, and the rate of change in the climate is something that hasn't been seen in the instrumental record or the geological records for many thousands of years. So the Earth is warming up. And New Zealand is no different to the rest of the world. We've been warming at about the global average rate, about a degree of warming or a bit more in the last century or so. But not everywhere is warming at that same rate. And generally speaking, land surfaces are warming up faster than ocean surfaces. So when you look at that and just calculate the change over land surfaces versus over the ocean, you find that the land has actually warmed up more than 1.5 degrees already, at about 1.6 degrees since the late 19th century. Meanwhile, the oceans have only warmed up about 0.9 of a degree, but less than a degree on average. So the reason for that is because it takes so much more energy to warm water compared to warming a land, soil. So you've got to poke a lot more energy into the oceans to get them to warm up. So it doesn't look as though the oceans have warmed a great deal, but they have absorbed vast amounts of energy. Over 90% of the total energy that's gone into the climate system from this increase in greenhouse gases has gone into the oceans. And as you'll no doubt hear from Tim soon, one of the main ways that's expressed is that the water column expands because it's warmer. So we get sea level rise because of this huge amount of heat that's been pushed into the oceans. So, all parts of the globe are being affected by climate change. And as things warm up, every 1/10 of a degree more warming, we get more impact, larger extreme events and so on. So we know that it's us doing this. We know that human activity is what, host does need to enable screen sharing. I'm sure we'll get there. Human activity is causing the climate change. We know from the composition of the atmosphere, the chemistry of the carbon, that it's burning fossil fuels that's causing all of this. And it's having a huge effect on extreme events, basically. And the reason that you feel this in extremes, you don't feel a 1/2 degree warmer every day. What you do feel is the really hot days. We have a distribution of temperatures. Most often you get something close to the average, but occasionally you get a really hot day, a really hot year, or a really cold day. And if you shift that distribution of temperatures a bit to the warm side, you can really pick up the number of hot days, and you start to get extremes that you just have never observed before, unknown heat waves. At the other end of the scale, you start to see less cold days. The number of frosts around the country has gone down hugely, less than half the number of frosts in most places now than there used to be back in the middle of last century. So that's the story with temperature. It's fairly straightforward. You shift the average to the warm side, you get a whole lot more high temperature extremes and many fewer cold temperature extremes. For rainfall, it's a bit of a different story. It's a more complicated picture. And it's amazing just how lumpy rainfall is. It doesn't fall evenly over the whole country. It doesn't fall evenly in time. You get big events, bang, and then it's dry for a long time. And it's amazing. Recent research has shown that on average around the globe, you get about half of your annual total rainfall in 12 days. 12 heavy rainfall events give you half of your rainfall for the whole year. So you tend to have these big dumps, and then you get long periods where it's drier. And climate change is affecting both ends of that scale. There's more moisture in the air when the air's warmer. So when it rains, there's more water to fall out of the sky. So you tend to get even heavier rainfall events. And we've seen that in this country recently to devastating effect. But at the other end of the scale, on those longer periods where it's dry, because the air's warmer, evaporation works better, soils dry out faster, and you get into drought conditions more quickly. So we end up with both heavier rainfall events when it rains and more intense droughts when it's not raining. And actually the days where you tend to get a bit of rain are getting squeezed out. We get more days of really heavy rain and also longer periods of dry. And this strange statistic of 12 days, 12 wet days giving you half of the total rainfall in a given place, and that number's expected to get smaller as time goes on because, you know, we get bigger dumps more quickly. I had a look at that for Timaru, and I happen to have a 50-year record of rainfalls at the airport. And yeah, for Timaru, half of the annual total rainfall falls in 14 days, so a little bit more than the global average, but not much. It's quite amazing. The 2 weeks where it rains, and that gives you half of your annual total. And if you look at the most recent 30-year period, we're down to 13 days instead of 14 days. So that doesn't prove anything, but it's consistent with that idea that we're getting more rain happening over a shorter period, giving us these bigger floods. So yeah, we've seen heat waves, floods, droughts, all sorts of chaos around the world, and also here in New Zealand. You know, the floods in Nelson recently and floods in Canterbury. It's everywhere you look in the media these days. So anyway, how do we stop this, and what do we do about it? I suppose is the real question. And I'm just going to try. Oh, no, I still can't screen share. That's fine. It's all about the amount of. Do you want to change the host to James Renwick? Yes, you do. It's all about how much more of this carbon dioxide gets put into the air. Oh, I'm the host. That probably means, oh, yes, I could share my presentation. Okay, why not? I'm just about out of time, and I'll jump to, where are we at? Yeah, there we go. All right, that's my opening slide. Let's go to slide number 11. Here we go. Yes. So here's my graphic of the carbon dioxide change for the last 13,000 years, the big spike towards the end when we started burning all those fossil fuels. How much higher is this spike going to get? And that will totally determine how much warming we get. We know that this amount of CO2 gives us about 1.1 degrees. And we know how much we're adding to the atmosphere every year. We know how much warming that'll give us. So it's quite easy to calculate that if we do nothing, we're going to be at 1.5 degrees of warming in 10 years, beginning of next decade. We'll be at 2 degrees of warming 10 years after that, roughly speaking. And we'd be at 3 degrees of warming 30 years or so after that. All of this is well before the end of this century. And as no doubt Tim will tell you, that this sort of level of warming has some major consequences in terms of ice melt and sea level rise, but also massive consequences in terms of the kind of extreme events. You know, we're already seeing these fires and heat waves and everything. That's at 1 degree of warming, roughly. What it looks like at 2 degrees or 3 degrees, I hate to think. But if we take action and reduce our emissions globally by half this decade, and get them down to zero, 100% reduction by 2050, that would still add up to the same amount of additional CO2 as doing nothing for a decade. So if we can get on top of it and take this action, you know, can we do this? We could stop the warming still at 1.5 degrees or something close to it. You know, we do actually have to get on, and all countries of the world have to make the 2020s this decade of action. Okay. So, statement from the IPCC, there's no going back from some changes in the climate, and this is the slow parts of the system, the oceans and the ice. But the atmosphere reacts very quickly. If we could stop emitting greenhouse gases, we could stop the warming almost overnight. Okay, extremes for Aotearoa. If we had a 2-degree warming in this country, that would translate to something like a tripling of the number of hot days here. And for Timaru, we're probably talking days above 25 or 30 degrees or so. If you had a month of those in the summer in the old climate, you'd have about 3 months of those in all of the summer under the revised climate. And the eastern part of the country is drying out a little bit, 5 or 10% less rain. Add that to a warming and you get something like a tripling of the occurrence of droughts, especially in the east of the South Island and the North Island, and also in Northland. And of course, warmer conditions with less rain, more drought goes with more chance of fires. So the fire season, the period where you're in this extreme or very high fire danger, increases by a factor of 2 to 3 in a lot of the eastern part of the South Island and elsewhere. So, you know, the consequences are pretty dire, but, you know, we can take action. We absolutely can take action. And the last part of the latest IPCC report that came out on mitigation, the Working Group 3 report, talking about what do we do to reduce emissions? Well, that said that we need to peak emissions, i.e. they can't go up any higher. They've got to start coming down before 2025, and it's already the second half of 2022, so we're talking in the next 2 years. And that would give us at least a coin toss sort of chance of keeping warming to 1.5 degrees. One thing I just want to emphasise, you know, we are the ones doing this. We are burning the oil and the coal. We are adding these gases to the atmosphere. We've got all the power to stop this. The climate isn't going to run away from us and blow up in our faces. Whenever we choose to stop adding these gases to the air, we'll stop the warming. So we just need to use that power. And there's all sorts of opportunities to reduce emissions from technologies we already have. Now, I'm not expecting anyone to read this picture, this graph from that IPCC report, just to point out that these are a list of options of things we can do to reduce emissions in all sorts of sectors, energy, buildings, industry, you name it. There's lots of things we already have at our fingertips to take this action. So we just need to be taking it. All right, just to wrap up. So we know that the climate's changing very fast. If we want to stop warming at 1.5 degrees, we need to make big reductions in emissions ASAP. Everybody's affected by this problem. Whether you're in Timaru or in Tuvalu or even in Siberia, you're feeling the effects. Many extremes. We're just seeing this on the news all the time now, just becoming more common. But just to re-emphasise, you know, we're the ones doing this to ourselves. We have the power to stop that change. We need to take that action. Okay, change in this country is near the global average rate. And that picture of the wet places becoming wetter and the dry places becoming drier is basically the picture for the future. But extreme rainfalls, heavy rainfall events becoming more intense and that's happening everywhere, regardless of what your average change looks like. And this has all sorts of implications for how we live our lives, essentially water availability, how we use land, agriculture. If you're living near a river that might flood or near the coast, low-lying conditions, we need to think about how to protect our infrastructure, our properties, or whether we need to move away from some of these regions. Okay, last point. I can't emphasise this too much. We need urgent reductions in emissions to stop warming, even at less than 2 degrees above pre-industrial. Action has to happen starting immediately. And it's very encouraging that we have an emissions reduction plan from the government in this country. We are at least at the starting blocks of getting the action going. Okay, so thanks very much. Sorry about the sharing problems earlier on. I'll stop there and happy to take a question if there's time. Cheers.
Thanks very much, James. If we could just go back to my slides for a minute, please. So we've had a question come in, James, from some of the people who registered here, and their question is, what's the ideal level of CO2 in the atmosphere and why? Back to you.
Oh, that's a great question. It's a bit like asking what's the ideal climate, and the answer is there is no ideal. In the past, carbon dioxide levels in the atmosphere have been several times what they are now, and during ice ages they're something like half of what they are now. And you know, there isn't an ideal level, or there isn't an ideal climate. It's all about what we're used to. Human civilization has grown up over the last 10,000 years or so roughly, and for most of that time, averaged around the globe, the climate was pretty constant. Sure, there was the little ice age and a few ups and downs, but they're pretty small compared to what's happening now. And so all of our food production, all of our agriculture, a lot of our infrastructure built near the coast because sea levels weren't rising. Suddenly that's all vulnerable. We have to move where we grow our crops. We have to move our big cities, a lot of them, the coastal cities, away from the rising shorelines. So it creates a lot of pain having all this change happening. So if I could wave a magic wand, I'd wind carbon dioxide levels back down at least to 350 parts per million and maybe closer to 300, something like the pre-industrial value, something like what the world was used to up until a few decades ago. Yeah,
thanks very much, James, and thanks for zooming in from Wellington. We're going to now move on to Professor Tim Nyish. So if I could just have that slide, please. Just before I do that, as I said before, we're going to ask you some questions and you can win some nice hampers. The first person that gives the answer that's within 5% of the correct answer is going to win the hamper. And Christine is going to give that person a couple of daffodils. And at the end of this evening, if you're holding those daffodils, you come over here and we'll take your details and we'll deliver that hamper to you. So that's how we're going to run this. It's a bit light-hearted. So the first question is this, and this is, what's the average estimate of how long ago the Earth's atmosphere contained more than 400 parts per million of carbon dioxide? So recently, with global warming and greenhouse gas emissions, we crossed over 400 parts per million of carbon dioxide in the atmosphere. When was the last time that happened? So put your hand up, give me an answer, and whoever gets closest to the right answer gets the prize. Any ideas? It's a worthwhile hamper. You get several packets of frozen vegetables, you get some potato chips, a number of pizzas as well. So we have an answer down here, sir. 10 million. 10 million, no, not quite, no. Anybody else? Over here? 3 million, closer. Keep going, anybody?
1 million.
No, going the wrong way now. 2 million. Well, too low, too low. Over here.
4 million.
Let's see, is that fairly close to 3.95? I think it is. Yes. So Christine's going to bring you a little bunch of daffodils over. So there's debate about these numbers. This is the number that the National Geographic came up with, and they said it's between 2.6 and 5.3 million years ago. At that point, the world was 3 degrees warmer. So that's how long ago it was when we got carbon dioxide up to the current level. It's long before any of us were born, isn't it? Pretty scary. Oh, most of us, sorry.